In this video, we're going to consider proof by induction. And proof by induction is a method we can use to demonstrate that a mathematical result is true. Anytime you see a mathematical result, that result has been proven to be true. Someone's demonstrated that that result is in fact true. And proof by induction is one of the ways, but not the only way, we can use to demonstrate that a result is indeed true. So we're going to work this example in a moment. We're going to prove this result is true using proof by induction. And proof by induction works really well for scenarios with summation, sigmas, series, infinite series, or basically when you've got a unknown or an infinite number of cases to prove to be true. Proof by induction, in terms of the method, works as a two-step process. So the first step is often called the basic step. And in the basic step, we're proving the result is true for the first case. So we're proving this result is true for, in this scenario, where n is 1. And normally that basic step is very straightforward, usually trivial, in fact. The more challenging part, especially if you're new to this method, will be the inductive step. And in the inductive step, we're trying to prove that the result is true for some n equals k plus 1, but only if it's true for n equals k. Or to put that the other way, to prove that if it's true for n equals k, that implies that it's true for n equals k plus 1. And what that means is, if you take some general case, the kth case, then that automatically implies it's true for the k plus 1th case. And this process is often likened to toppling dominoes. If you've got dominoes lined up and you know they're definitely lined up, if you topple that first domino, it will just hit the second one, and the third, and the fourth, and they'll all basically follow. So this is like proving that your dominoes are lined up, the inductive step, and the basic step is like toppling over that first domino. So we're going to work this example in a moment. Before we work this example, let's just think about what this example actually means. These proof by induction methods can be used on any type of proof. This one happens to be to do with a series. This is saying that if you take the sum from r equals 1 to n of r, the result comes out to be 1/2 n times n plus 1. So for example, if we let n equal some actual value, so if we let n equal 5, say, then that's going to be the sum from r equals 1 to 5 of r. Remember, this r in here is just a placeholder. It's just telling you what to do with the numbers. In this case, we're just taking the numbers and adding them together. So that would be 1 plus 2 plus 3 plus 4 plus 5. And that is 3, 6, 10. That comes out to be 15. Now that was actually quite straightforward to do. But imagine if that r value, that n value, sorry, became 10. Or 20, or 100, or 1,000, or 1,000,000, it would become cumbersome to make this calculation. This formula says, well, you don't need to do the calculation, you can just put your n value in here and work out what you get. So let's just test that that does actually work. So if we take 1/2, this time we're changing our n to 5, so 1/2 times 5 times 5 plus 1. So that's going to be equal to 1/2 times 5, 5 plus 1 is 6, so times 6. 1/2 times 6 is 3, 3 times 5 is indeed 15. So that comes out to be the same result. So that's just a demonstration of what this result in this case actually means. Now we want to go ahead and use proof by induction to show that this actual formula, the original formula we've just used there, is indeed true. So always remember, when you're doing proof by induction, you've got to go through the two steps. So we're going to start with the basic step, which is, like I say, normally fairly trivial. So in the basic step, we're trying to prove the result is true for the first case. The first case in this example is when n is 1. So you're basically letting your n equal 1. So that would be the sum from r equals 1 to 1 of r. But that's just one term. That's just that first term. So that is just equal to 1. And you're done, right? That's just the first term. We want to prove that that is true for the formula. So we're going to work the sigma. We've worked the sigma part on this side, we're going to work the other side of the formula over here. We're just letting the n value be 1, so it's going to be 1/2 times 1 times 1 plus 1. So we're just plugging 1 in the place of the n in the formula, just like we did here with the 5. 1/2 times 1 is 1/2. 1 plus 1 is 2, so it's going to be 1/2 times 2, which equals 1. So these have come out to be the same value. So that means that we can sort of validate, sign off on the basic step being true. The basic step is usually quite a small amount of working. I want to move on and have a go at the inductive step, which is definitely more challenging. And at first, the inductive step, if you've not seen proof by induction before, it will seem weird, right? It will just take a while to get used to it. The important thing here is that we're going to assume this result is true, which means that at some point in our working, we'll need to pull in or use that assumption, but we're trying to prove that it's true for the next case. What this actually means in practice is that our assumption is that when n is equal to k, the result is true. So if you change the n to a k, then our assumption is going to be like this. So we're allowed to assume that the sum from r equals 1 to k of r is equal to 1/2 k plus 1. So notice that that is just the result we had already, but changing the n's to a k, and that's a result that at some point we need to use in our working. But what we're trying to show is that this implies that if that is true, this implies that the result is true for k plus 1. In other words, r equals 1, the sum r equals 1 to k plus 1 of r is going to be equal to 1/2 k plus 1, k plus 1 plus 1. So it'll be 1/2, changing the k to a k plus 1, changing this k to a k plus 1, so it'll be k plus 1 plus 1, which is k plus 2. So that's the result we're trying to show to be true. Now this that I've written down here, this here is not part of our working, it's kind of side working. You wouldn't need that as part of your answer. It's just to kind of guide you along, because it's easy to get lost in the algebra in these questions. So this is what we're trying to show to be true. So let's start with this here, this left-hand side. So it's going to be the sum from r equals 1 to k plus 1 of r. And these questions where you're using proof by induction, they don't have to be about infinite series or finite series. They can be about anything, but if it is a case where it's to do with a series, which a lot of them are, it's a common trick to split your series as the sum from r equals 1 to k. In fact, it's not a trick, it's something you've got to do. So it's r equals 1 to k of r. And so that would give us the terms all the way from 1 right up to k. We've got k plus 1 terms, so we've only got one more term, and it's the final term, it's the k plus 1th term. So I'm just going to write this in. You wouldn't normally write this in, but just for demonstration, the thing we're going to add to this is the k plus 1th term. The final term, if you like, in the series. A little bit like splitting the sum from 1 to 5 as a sum from 1 to 4, and then adding on the 5th term, which would be 5 in that case. So what does that k plus 1th term look like? Well, it's just r replaced with k plus 1 in this particular case. So that's going to be the sum from r equals 1 to k of r plus k plus 1. But this part here, the sum from r equals 1 to k of r, is the thing that we are allowed to use as our assumption. This is where we're going to pull in that result. So this part here we know to be just 1/2 k plus 1. That's for this bit. K plus 1 on the end is just going to stay there, k plus 1. Keep an eye on where you're trying to get to. We're trying to get to this here. So there's always a little bit of algebra in these questions, and it's not always easy. It might take a bit of experience. But notice here there's a common factor of k plus 1. So you could start by pulling out the common factor. There's different ways you could finish this question off. If you pull out that common factor, if we then use a bracket, we would need a 1/2 k for our first term, and we would need a 1 for the second term. So k plus 1 times that gives you that. K plus 1 times 1 gives you that. So that's a factorising complete. Notice that in the final answer, they've got a 1/2 in front. So what I'm going to do, I'm going to keep my k plus 1 term, because there is a k plus 1 term in the final answer. But what I'm going to do is introduce a common factor here of 1/2, which would then look like this. Now this might look a little weird, and like where did that come from? But if you think about it, 1/2 times k is 1/2 k, 1/2 times 2 is 1. So I've just rewritten the 1/2 k plus 1 like this. But the reason why I've wanted to do that, that now introduces the terms that we need in our proof. So just by reordering those, that'll be 1/2 times k plus 1 times k plus 2. So down here we proved that the basic step was true, that trivial step. Here we've now proven that the inductive step is true. So that completes the proof. So now we can say that that result is indeed true. This whole inductive step will be tricky at first. And my main advice to you would be to understand the method, first of all, what you're trying to achieve, but also just to work a bunch of examples. It's definitely something that you need to do rather than just sort of theorizing about. It is quite useful to write down what it is you're trying to assume, or what it is you're going to assume, and what it is you're trying to show, because this gives you an end goal. That's where you're trying to get to. You're trying to get from here to here. So we started there, the left-hand side, and we developed it into the right-hand side. But the important thing is that at some point, you'll need to use your assumption. That's our assumption there. That's what we pulled in from over here. So that's how we prove that result using proof by induction. We want to use proof by induction to show that this result is true. And proof by induction, remember, is a method you can use to demonstrate mathematical results are true, and it's a two-step process. The first step, often called the basic step, is usually trivial. It's showing that the result is true for the first case. The first case in this example is where n is 1, so our basic step here would be showing that that result is true when n equals 1. The more challenging part, and it can be quite challenging, is the inductive step, where we're assuming the result is true for some general case, like the kth case, and showing that that implies the result is true for the next case, the k plus 1th case. So let's just crack on and have a go at this one. So we'll start obviously with the basic step. The basic step, you are just basically plugging in the value. So in the basic step, we're going to let the n value be 1 because that is our first case. Okay, and we want to deal with whatever that first case is. So we want to work out the sum from r equals 1 to just 1, which is unusual, but just 1 to 1, of 3 to the power of r minus 1. So there is only one r value here, which is 1, so that's going to be 3 to the power of 1 minus 1, which is 3 to the power of 0, but anything to the power of 0 from exponent rules equals 1. So that comes out to be 1. We want to check that that's what we'll get if we put a 1 in here for n as well. So that right-hand side, if you like, that's going to be 1/2. It's really just a numerical thing, mostly, when you're using the basic step, the first step in proof by induction. So 3 to the power of 1 this time, minus 1. 3 to the power of 1 is just 3. 3 minus 1 is 2. So that becomes 1/2 multiplied by 2. 1/2 multiplied by 2 is 1. So those have come out to be equal. That's what we expected. So that's fine. So we can sign off on the basic step, which is the more trivial part. The more challenging part of the inductive step, it might be worth writing out what our assumption actually is and what it is we're actually trying to show. So we're assuming that this is true for the general kth case. So in other words, if we change that to a k, so that's basically, we're allowed then to assume that the sum from r equals 1, not to n, but to k, of 3 to the power of r minus 1. The 3 to the r minus 1, that's just our kind of formula. It's like the placeholder, I guess, equals 1/2 bracket 3 to the power of k this time minus 1. So all we're doing in that assumption is replacing the n basically with a k or some other letter, but we often use k. What we want to then do is that if that assumption is true, we want to show that that then implies that the sum from r equals 1, not to k, but to k plus 1 of 3 to the r minus 1 equals 1/2, but instead of 3 to the k, 3 to the k plus 1 minus 1. Okay, so that's what we're trying to show. This is not really part of the working, this is just kind of side working, but it is useful to write that down. This gives us a target, and it also reminds us that on the way to that target, as part of the process, we'll need to use this assumption. Otherwise, we're not using proof by induction. You've got to use your assumption at some point. So I'm just going to make some space here. So that was the basic step over here, and we'll work on the inductive step. So this is where we're starting. We're starting here and trying to turn that into that. So it's going to be the sum from r equals 1 to k plus 1 of 3 to the power of r minus 1. So proof by induction questions are not always to do with series, but they often are. If it is a series and you're making this k plus 1th term, then a common trick, in fact really the only way you can do it, is to split that. So the sum r equals 1 to k of 3 to the power of r minus 1. So that's your first k terms. But remember, there's k plus 1 terms here, so we need to include that final term, that k plus 1th term. That final term is just this thing here, but with a k plus 1 in the place of the 3. So it's going to be plus that final term which is 3 to the power of k plus 1, and you've still got the little minus 1 there, okay? So it should be that after some working, and it's not necessarily easy working, we somehow get from here all the way to that result that we're looking for. How you get there really depends on the question. They require different types of algebra. You've really just got to gain some experience. Let's have a look at this one. So the first term we're just going to maybe leave for the time being. So that's the sum r equals 1 to k of 3 to the r minus 1. This one we can tidy up. So the 1, positive 1 take away 1 is obviously just 0. So that just becomes a 3 to the power of k. So it's plus 3 to the power of k. But notice at this point, because we've split our summation 1 to k plus 1 into these two parts, this first part here is now matching up with our assumption. This is where we can pull in our assumption. So we know what this is equal to. It's equal to 1/2 3 to the power of k minus 1. So that is equal to 1/2 bracket 3 to the power of k minus 1. And then we've still got that 3 to the k just hanging out on the end there. So remember, it's worth always keeping an eye on where you're trying to get to. It's not always obvious how you're going to get there, but keep an eye on it. So I'm going to take this out of the bracket. It's not obvious you need to take it out of the bracket, but if you notice it, this bracket is not the same as that bracket, so it's not worth keeping it in the bracket. If we do take it out of the bracket, it's going to be 1/2 times 3 to the k, and then 1/2 times minus 1, which is just minus 1/2, and the 3 to the k is just on the end. And again, I will emphasize a point that it's not obvious how to get to the answer in these. It will take a bit of practice and experience. In this particular case, we can reorder the terms. So I want to pool these two terms with the 3 to the k together. So it's going to be 1/2 times 3 to the k plus 3 to the k minus 1/2. So all that I've done there is reorder the terms. But I've done that because now we can pull out here a common factor of 3 to the k. So that would be 3 to the k bracket 1/2 plus 1. So 3 to the k times 1/2 gives you 1/2 times 3 to the k. 3 to the k times 1 gives you 3 to the k. So that is the correct factorization. And then we've got minus 1/2 on the end. This here, though, is 1/2 plus 1, which is 1/2, or 3 over 2. So this becomes 3 to the power of k times 3 over 2 minus 1/2. And if you think about that 3 over 2, that 3 on the top there is a 3 to the power of 1. If you're multiplying a term to a fraction, you just multiply it to the top of the fraction. So this is like 3 to the power of k times 3 to the power of 1 all over 2 minus 1 over 2. So you might start to see where this is going. And then this is going to give us, because of exponent rules, 3 to the power of k plus 1, because you multiply by adding the powers together, 3 to the power of k plus 1. I'm just going to leave that over 2 minus 1 over 2. But you can see now these have got a common factor of that over 2 part. In other words, a common factor of 1/2. So I can pull that half in front. So we get 1/2, 3 to the power of k plus 1 minus 1. And that is what we were trying to get to. So tricky algebra in the middle, and you will need to gain experience to know how to do that algebra. But just notice that we've now completed the overall proof. We did the basic step over here, that trivial step, proving that the first case was true. And in the inductive step, we've now just proven that if we can assume that the general kth case is true, that implies that the next case, the k plus 1th case, is also true. And that completes the proof by induction for that particular result. We want to show that this result is true using proof by induction. Remember that proof by induction is a two-step process. We start by showing the result is true for the first case. That's often called the basic step. And the basic step is generally quite straightforward. Then we have got the inductive step, which is the more challenging part of the proof. That's where we assume the result is true for some general case, like the kth case, and show that that implies the result is true for the next case, the k plus 1th case. So without further ado, let's go on with this example. So we'll start with the basic case. The basic case in this basic step, in this case is when n is 1. So we're just going to let our n value equal 1. So we're trying to show that the left-hand side is equal to the right-hand side when n is 1. So we're going to take the sum from r equals 1 to just 1, which looks a little bit odd, but that's often how these are in these proof by induction questions. And this question involves factorial, so we've got r factorial multiplied by r. We're putting in only 1 because this summation is running from just 1 to 1, so it's just going to be 1 factorial times multiplied to 1. So I'll maybe just use some brackets here, 1 factorial times 1 like this. 1 factorial is just 1, 1 times 1 is just 1, so that just comes out to be 1. Just a general point on factorials, if you're not used to those, so something like 5 factorial is just notation that means 5 multiplied to all the numbers below 5, so 5 times 4 times 3 times 2 times 1. In general, n factorial is n times n minus 1 times n minus 2, all the way down to the 3 times 2 times 1. So it's capturing all the numbers below it. So that there would be the left-hand side. We want to show that's equal to the right-hand side. So the right-hand side is when n is 1, we're going to get 1 plus 1 factorial. So 1 plus 1 factorial minus 1. 1 plus 1 obviously is 2, so that's 2 factorial minus 1. 2 factorial is just 2 times 1, which equals just 2. So that's just 2 minus 1, which is 1. So these are equal, so that completes basically the first part, the basic step. So we've shown that for the first case, this result is indeed true. Now the more challenging part we want to work up is the inductive step. So it's useful, not needed, but useful as part of your working to maybe just write out more fully what these are. So we're going to assume that this result is true for the general case n equals k. That really means just replacing the n's in this original formula with k. So we're going to assume that the sum, just put it here, so we're going to assume that the sum from r equals 1 up to k of this expression r factorial r, so r factorial r, is equal to k plus 1 factorial minus 1. So k plus 1 factorial minus 1. So that's our assumption. We need to use that as part of the inductive step. If you find yourself doing one of these and you don't use your assumption, or you don't have an assumption, then something's gone wrong. You need to use that, and we're going to use that later on in our working. We then want to use that assumption to show the result is true for the k plus 1th case. So that's going to be the sum r equals 1 to k plus 1 of r factorial r. And basically we're just replacing the n with a k plus 1 this time. So that's going to be k plus 1, which will be k plus 2 factorial minus 1. So that's got to come out to be k plus 2 factorial minus 1. If we complete this step, then the whole proof will be complete. So I'm just going to put this in a sort of bracket just to show that's not really part of our work, and it's just our kind of guide. Okay, so this is what we want to show. We want to start with this here and somehow show that we can turn that into that. So we're starting with this guy here. So it's going to be the sum from r equals 1 to k plus 1 of r factorial r. This is a sum from 1 to k plus 1. We're going to split that as a sum from 1 to k plus that final term, the k plus 1th term. So it's going to be the sum, and this is a really common method in questions involving summations, and we'll split it to the first k terms, and that's really so that we can then use our assumption. So the sum from r equals 1 to k of r factorial r plus that k plus 1th term, that final term. But the final term is just when you take this guy and substitute in the final term, which is k plus 1. So that's going to be k plus 1 factorial times k plus 1. Okay, it's not easy. It looks a little bit clunky. It does take a bit of experience to get used to these. This, though, now matches up with the part we're allowed to assume. In other words, it matches up with this guy here. So we know from our assumption that this is just equal to k plus 1 factorial minus 1. So I'm just replacing this summation with this guy here. And then these guys are just the same. So k plus 1 factorial times k plus 1 like this. This is always the challenging part, is how do I now get from here to here? Depends what the question's about. These questions could be about a wide range of different things. How you get from there to there really does depend upon your algebraic, how you see it algebraically. People go about these in different ways. There are different ways to do them. Sometimes you just got to play around with the options until you get where you need to be. So one thing I'm going to do here, I'm just going to put this minus one term on the end, because here we've got a term. So we've got three terms here. 1, 2, 3. This is all one term. These two terms have got a common factor of k plus 1 factorial. So I'm going to want to group those together so that I can then use that common factor. So I'm just rewriting this as k plus 1 factorial plus k plus 1 factorial times k plus 1, and then we've got a minus 1 tagged on the end like that. It's always worth just keeping half an eye on where you're trying to get to see if you're sort of moving in the right direction, although it can be tricky to sometimes to see how you're going to get from there to. You've just got to kind of go with the algebra. Common factor here of k plus 1 factorial, so k plus 1 factorial, which seems like an odd common factor, but again, it's just something we need to get used to. And then we're going to open a bracket, and I'm going to use a square bracket, and inside that bracket we need something for this term, which would be just a 1, something for this term, which would be a k plus 1, like this. The minus 1 is not part of the common factor, the factorising process, that just hangs out in the end. Just checking that factorising, so this guy here times 1 gives us that, and this guy here times k plus 1, which you could, if you want, put in a bracket. This guy here times that gives you that term. So that is the correct factorisation. But you can see now that the inside of that bracket becomes a k plus 2, okay? Just a k plus 2, don't need the square bracket anymore. And then we've got a minus 1 on the end. So we're fairly close now to getting where we need to be. We've kind of got that minus 1 on the end, but we don't have a k plus 2 factorial. We've got a k plus 1 factorial and a k plus 2, just a normal k plus 2. So how do we get to there? Well, this is where, in this particular question, you would need to think a little bit about the factorials. So maybe just a bit, as a bit of side working, I'll do that over here. So if we think about what that is, so k plus 1 factorial times k plus 2. So the order in which you multiply things doesn't matter. So I'm just going to reorder those to put the k plus 2 term first. So we're going to get k plus 2 bracket k plus 1 factorial. K plus 1 factorial though, remember I said about the factorials that it just multiplies to every number below it. So 5 times 4 times 3 times 2 times 1 in the case of 5 factorial. But notice that each of those numbers is 1 less than the previous number. So k plus 1 factorial, in fact let me just write the k plus 2 first, but the k plus 1 factorial just starts with k plus 1, and then it's got the next term below that, which would be a k, and then it's got 1 less than that, which is k minus 1, and then it keeps going all the way down until you've eventually got, say, a 3, and that would multiply to a 2 times a 1. So it just captures that. But if you notice what we're now left with, we've now got k plus 2, then k plus 1, then k minus 1, and that goes all the way down to 1. In other words, these are still now in a perfect sequence where you're taking 1 off every time, because k plus 2 take away 1 gives you k plus 1. So this guy here, all of this, is in fact k plus 2 factorial. So this here, k plus 1 factorial times k plus 2, is actually equal to k plus 2 factorial. So that result, you're going to need to know a little bit about factorials. But if I then pull that over here, we get k plus 2 factorial for these guys, minus 1, and that's the result that we were trying to prove. So that gives us our second step, the inductive step. And that completes the proof by induction. Proof by induction is not easy. You need to learn the overall steps. You need to learn what you're looking out for. Every question is also going to be a little different. So it does take a bit of practice and a bit of experience.